Hello, everyone. Today, Braun Academy will be presenting to you conceptual derivatives and how they pertain to AP Physics C. First, we must answer the question, what is calculus? Calculus is known as the branch of mathematics concerned with the properties of the changing of functions, often considered the mathematical backbone for dealing with problems where variables change with time. Physics is known as the study of the natural properties of matter and energy. While appearing to be initially unrelated, calculus is a very helpful tool to use when studying physics. Lessons covering this course will include those of conceptualizing derivatives, applying derivatives, conceptualizing integrals, and applying integrals. But today, what you'll need to focus on is the conceptualizing of derivatives. First, we must answer the question, what is a derivative? Well, a derivative is the instantaneous rate of change, essentially what a slope is at a point. You already know that a slope is the average rate of change between 2 points. Well, a derivative is that same thing except 1 point. As you already know, the slope of function can be calculated by having the rise of the function divided by the run of the function. As shown in this example, we can use the different coordinates for b and a to estimate the slope that would be at c. However, using the slope to estimate the midpoint between 2 points cannot always be super accurate. If we use the slope between 2 points to estimate what c would be, we would get that it's 26 over 6, whereas the actual slope at that point is 2. This is where calculus can come in handy when calculating the instantaneous rate of change at a singular point. Now you may be asking yourselves, why do derivatives matter when you could use slope in order to calculate them? Well, as you saw earlier, slope is only an approximation. It's not an actual value for the instantaneous rate of change at a point. It's very limited and can be very time consuming compared to taking a derivative. Why does this matter in terms of physics? Well, in physics, we deal with motion. This can relate to calculus as a position of a object can be related to the x of the function. The velocity of the function is the derivative of that position function being f prime or v velocity of t, and the acceleration is the double derivative of that, or double dash, if you will, otherwise known as a of t. Knowing how to derive, uh, knowing how to derive the derivatives of different functions can make physics very. So I'm sure you may be asking yourself, how do you take a derivative? Well, I'm glad, because I'm here to tell you. As you can see here, this function has a singular, unchanging slope. It doesn't change as it increases. Therefore, the derivative function is a singular line intersecting through the point of its value, otherwise known as 1. Here's where you get the first idea of how to take a derivative. While the two functions may not be very similar in appearance at first, what you will soon learn is that the function on the right is actually the derivative of the function on the left. How do you take this derivative? Well, I'm glad you asked. This derivative was taken using the power rule. In order to do the power rule, you must move the exponent down in front of the variable, multiply by the coefficient of that variable if there is one, and decrease the exponent by 1. As shown in the example on the bottom, x squared can be changed into 2x by taking the initial exponent 2, moving it down to the in front of the x, and subtracting 2 by 1. So you get 2x to the first, which we all already know is 2x. Another rule of deriving equations is that of the chain rule. In order to perform the chain rule, you must take the derivative of the function outside of the parentheses, then take the derivative of the function inside the parentheses, making sure to multiply the two together. As you can see here, when we have the function f of x all raised to the exponent n, we must first take the exponent of n, subtract it by 1, and multiply in the front, just as we learned in the power rule. But however, we still have the function inside that has not been derived yet. Therefore, we must multiply that the whole derivative that we have just created by the derivative of the f function. This is further exemplified in the second example, where we have f of g of x, where we take the derivative of f prime, and still in terms of g of x, and then multiply that by the derivative of g prime of x. Here are a few examples of some of the ways to take derivatives. As you can see, we have the power rule right here in the third down on the formula sheet labeled calculus. Then we have another example of a way to take a derivative, that of the ln of a of x, which the derivative of which would be 1 over x. Also, a helpful mm, knowledge is that the derivative of sine is cosine, and making sure to have a of x being done with the chain rule so that you can know what to do with a constant in front of the variable x. Another good thing to know is that the derivative of cosine is negative sine. With this knowledge, let's take the time to do a few practice problems. Now, the first question that we'll go over is question 8. It deals with a 0.5 kilogram rubber ball initially moving at a speed of 10 meters per second in the positive x direction toward a stationary wall, as shown above. The ball bounces back off the wall with a speed of 5 meters per second in the negative x direction. Which of the following best represents the rate of change the ball's momentum, dp/dt, as a function of time? Well, according to your formula sheet, little p, which is known as momentum, is equal to mass times velocity. Since the mass of the ball does not change, staying constant at 0.5 kilograms, the only thing that changes would be the velocity, which changes from 10 meters per second to 5 meters per second. The derivative of velocity, as we said earlier, is acceleration. Therefore, since the ball is slowing down from 10 meters per second to 5 meters per second, we know that the acceleration of the ball will be negative. The only one of these answers that has a entirely negative acceleration is that of B. So that will be our answer. A particle of mass m moves from the point A to point B along the path shown in the diagram. At each of the four labeled points, the net force on the particle is represented by a vector. How can one tell that the kinetic energy of the particle is increasing at point C? Well, based on your formula sheet, we know that force is equal to mass times acceleration. We also know that kinetic energy is equal to 1/2 squared. So, that is a terrible m, my bad. Since mass is unchanging throughout the problem, we know that the only thing changing is that of the velocity and acceleration, so we can use that to help solve our problem. We also know that the derivative of velocity is acceleration, so we can also use that to help us solve our problem. So, looking at all of the answers, we see that A says that the net force has the greatest magnitude at point C. This is simply incorrect, as we can see that the net force of A is much larger than that of C. For B, we can see that the net force and V are nearly parallel at C. This is correct, so therefore we will put this away for later. We see in letter C, the speed is at least at C. We don't necessarily know this. Well, this is also not true, because the velocity at A is larger, so no. The particle is going downhill at sea. We're not given the different types, or we don't know what if this is a hill or not. So this is also a bad answer for us to pick. And then we get to E, which says the net force is not in the direction of motion at other points. While this is true with points A, B, and D having force vectors that are pointing away, this isn't the full correct. This isn't fully correct, and as it doesn't fully explain why the net force V is the largest, that being that they're parallel. So therefore, B would be the answer.
Question 24. The position of the position x of an object is given as a function of time t by the equation x equals 8 plus 4t minus 6t cubed, where x is in meters and t is in seconds. What is the maximum positive velocity attained by this object? Since we have the position function, we can take the derivative of that and find the velocity function. And in order to find the critical values of the velocity function, we have to set that velocity function, we have to take the derivative of that function and set the derivative equal to 0, because that's how we find critical values of a function in calculus. So having done that, we get that x double prime is equal to 36t. And setting that equal to 0, we find that t equals 0. So that means that at t equals 0, x prime of t is at a critical value, so either a maximum or a minimum. Plugging that in, that means that the maximum velocity of the function equals 4 meters per second, and so our answer is A.
Question 25. The position of a toy locomotive moving on a straight track along the x-axis is given by the equation x equals t cubed minus 6t squared plus 9t, where x is in meters and t is in seconds. The net force on the locomotive is equal to 0 when t is equal to what? Well, we know, given Newton's second law, F equals ma, that force would be 0 when acceleration is equal to 0. And therefore, we take the two derivatives, the first being velocity x prime equals 3t squared minus 12t plus 9, and the second, x double prime, being the acceleration, equal to 6t minus 12. So all we have to do now is set x double prime equal to 0 and find that 6t equals 12, so therefore t is equal to 2, which would be B.